Hello everyone, my name is Enrico Aperno. I'm currently a technical student at CERN working on CO2 cooling, and I'm creating this YouTube series to pass on the information I've learned in the past year to future incoming students. So the series will be divided into three main parts. The first video being this one, I'll be discussing why we use cooling at CERN. Then I'll be discussing some refrigeration basics, such as the vapor compression cycle and the CERN unique refrigeration cycle, which is the two-phase accumulator control loop, or two-PACL. And finally, I'll be discussing why we use CO2 as a refrigerant. In the second video, I'll be giving a deeper dive into two-PACL and discussing how cooling is distributed. And finally, I'll be giving another video introducing Refprop, an engineering software that can be used to extract thermodynamic properties of refrigerants. Here I'll give a very crude overview of what happens at CERN and why we use cooling. So as you know, the LHC accelerates protons nearly the speed of light and collides them in main detectors, such as ATLAS and CMS. We also have some other detectors along the LHC, which are the LHCb and VELO detectors. Inside the detectors, sometimes the protons collide, and as a result, new particles are formed, such as the Higgs boson. The Higgs boson has a very short lifetime, and in reality, what we're measuring are the decay particles from the Higgs boson, not the Higgs boson itself. These decay particles are usually photons, electrons, protons, or muons. The detectors are meant to measure these particles' types, energies, and trajectories. So the ATLAS detector can be divided into three main components, being the inner detector, which measures the trajectories of charged particles. Then we have the electromagnetic calorimeters, which measures the energies of particles. And finally, we have the muon chambers, which measure muons. The inner detector is composed of silicon. And because of the high radiation inside the detector, the silicon degrades over time and is damaged. However, we can shield the silicon from radiation by a process known as the Losar's effect. When we cool silicon to temperatures around -40 degrees Celsius, we can shield the silicon from high radiation doses. So to become familiar with refrigeration, you'll have to know the pressure-enthalpy diagrams. And this pressure-enthalpy diagram that we're sketching is for CO2. Enthalpy can be thought as heat or energy of the refrigerant. So the pressure-enthalpy diagram divides the refrigerant into different phases. So this leftmost region is the solid phase. In the middle region, we have liquid. And to the right, we have gas. This upper right region is known as supercritical. With this point being the critical point, and this point being the triple point, where the solid, liquid, and gas phases coexist. This triple point is at -57 degrees Celsius. These regions which have length are known as two-phase regions. So for example, in this region here is where boiling occurs. Here we have solid gas, and here we have solid liquid. We can also sketch some isothermals on this graph, where the temperature is consistent. So here we have, for example, 25 degrees Celsius isothermal. And here I can sketch the -40 degrees Celsius isothermal. I can also draw vapor quality lines, which describes the ratio of the two different phases in this liquid gaseous region. So for example, in this middle line, we are exactly 50% liquid and 50% gas based on mass. The most basic refrigeration cycle is the vapor compression cycle, and this can be used, for instance, in air conditioning. So on the left here, we have a simplified piping and instrumentation diagram, and we'll follow the P&ID along with the pressure-enthalpy diagram. So the cooling happens indoors in what is known as an evaporator, which takes warm air and cools it. Outdoors, we will find the condenser, which does the opposite, which takes outdoor air and slightly warms it up. So as you know, cooling happens when gas is expanded. So for example, at point 1, we're expanding and as a result decreasing the refrigerant. This causes the temperature to drop. Then in the evaporator, we're taking warm air inside and cooling it down. As a result, we're increasing the energy of the refrigerant. Next, the refrigerant will pass through a compressor, which increases the pressure. And the best it can do is this isentropic curve. And finally, the condenser will take warm air outside and warm it up by a little bit. So for instance, the warm air outdoors is 25 and it'll increase to 30 degrees Celsius. So now I'll be giving a big picture overview of the CERN unique refrigeration cycle, which is the two-Packel loop. So inside the experimental cavern is where the detectors are placed, and as a result, there's a very high radiation dose. All the plant components here are entirely passive, that is just tubing. On the other hand, we have a service cavern, which is separated by a thick wall, and here's where the active components of the plant are, such as the pump, chiller, and any other electronic components. Here, I drew the evaporator as this semicircle. So these orange bits here I drew as the silicon sensors, and they're actually measuring the charged particle trajectories. As you can tell, half of the diagram is drawn in dark green, while the rest is drawn in blue. The dark green represents where the refrigerant is two-phase, and blue represents where the refrigerant is liquid. The reason why we use two-phase at the evaporator is because two-phase has isothermal properties, which means that at the inlet and outlet of the evaporator, we are at the same temperature, because as you're boiling, the temperature remains consistent. Also, two-phase has a high heat transfer coefficient, which means heat from the silicon sensors is efficiently transferred inside to the refrigerant. So in the next slide, I'll be discussing the two-Packel loop in comparison to a Pressure-Enthalpy diagram. But for now, let's just label the main components. So here we have the pump. Then we have the main transfer line, which transports the CO2 from the service cavern to the experimental cavern. Then we have the capillaries and the accumulator. And finally, the chiller, or let's say condenser. So the main chiller is an independent refrigeration cycle, which helps the two-Packel. So the main chiller is usually a vapor compression cycle. So now let's walk along the two-Packel loop with the help of a pressure-enthalpy diagram. Let's start our pressure-enthalpy diagram at point 1, which is when we're subcooled and the refrigerant has just been condensed by the main chiller. So this is point 1. And the pump increases the pressure of the refrigerant. And also because of its imperfections, it also adds a little bit of heat to the refrigerant. Then the main transfer line is a heat exchanger, which I'll be discussing later. But for now, trust me in saying that the refrigerant is increasing its enthalpy and thus heating up a little bit. Then the expansion happens inside the capillary. The capillary is a very thin pipe of inner diameter on the orders of 1 millimeter. So here we're expanding the liquid, and as a result, bringing it down to the saturation line. Inside the evaporator, we are boiling the refrigerant, and thus keeping the temperature more or less constant. I say more or less constant because in reality, while we're passing the refrigerant inside the evaporator, its pressure is slightly decreasing due to frictional pressure drops, and as a result, the boiling temperature decreases. And so from 0.4 to 0.5, we are actually cooling down the refrigerant. Then we are passing back inside the main transfer line, which transports, once again, the CO2 from the service cavern to the experimental cavern. And this heat is exchanged with points 2 to 3. As a result, these two lines are exactly the same length, since the heat is exchanged between them. Finally, from point 6 to 1, the refrigerant is condensed further by the main chiller, and we return back to point 1. So the reason why there's the accumulator in along this loop is to control the temperature along the evaporator. Because we're in two-phase, by controlling the pressure of the vessel, we are actually controlling the temperature along the evaporator. So since here we have lines of equal pressure and lines of equal temperature, by adjusting the pressure, we can actually adjust the temperature. So the pressure inside the accumulator can be increased by using heating rods and decreased by cooling it down with the aid of the main chiller. Finally, I'll be discussing why we use CO2 as a refrigerant at CERN. The first reason being it has favorable thermodynamic properties. So inside the capillaries, these pipes of inner diameter around 1 millimeter, the fluid needs to have low viscosity at low temperatures, which CO2 has. Furthermore, CO2 has a high heat transfer coefficient at the two-phase boundary, which is required for the silicon sensors. Also, the operating temperature is around minus 40 degrees Celsius, which is above the freezing point of CO2, which is minus 57 degrees Celsius. Furthermore, CO2 is non-toxic and non-flammable, which makes it safe to use inside the experimental cavern. And compared to other refrigerants, CO2 is a much weaker greenhouse gas, and as a result, its global warming potential is much lower. So that concludes this first video, and I hope you watch the next ones. Thank you.